Let ABC be an equilateral triangle with side length 8. Let x be on side AB such that AX equals 5, and let y be on side AC so that AY equals 3. Let Z be on side BC such that AZ, BY, and CX are concurrent. Let ZX and ZY intersect the circumcircle of AXY, again at P and Q respectively. And let XQ and YP intersect at K. Compute KX times KQ. So we have equilateral triangle ABC here with side length 8. Points X and Y lie on sides AB and AC, with AX equals 5 and AY equals 3, and point Z is the unique point on side BC, where AZ, BY, and CX are concurrent. We're going to let ZX and ZY intersect the circumcircle of AXY, again at points P and Q. So point P is here, and point Q is here. And also we're going to let XQ and YP intersect at point K. These lines intersect at point K, probably somewhere down here. Yeah, that's point K. And we want to find KX times KQ, which is none other than the power of point K with respect to the circumcircle of AXY. We look at this diagram, and we see that it's definitely a projective problem. So we're going to have to use projective geometry to solve this problem, obviously. But first, let's make a few observations before we go anywhere near point K or any of the other points, even P and Q. Let's start with the basics. Only triangle ABC points X, Y, Z in the circumcircle of AXY. It appears as though the concurrency point of these three Chevians here, AZ, BY, and CX, let's call that point D. It appears as though point D lies on the circumcircle of AXY. Now, is that really true? Well, note that triangles BYC and CXA are concurrent. By symmetry, because this is an equilateral triangle, CX and BY have the same length. AC and BC obviously have the same length. And yeah, AX is equal to YC. So yeah, the two triangles are congruent. So we can write the triangle BYC is congruent to triangle CXA. And we can mark some equal angles here. Angle BYC is equal to angle CXA. So this angle is equal to this angle. Now we can do pi minus this angle and we get this angle. And we have that angles AXC and AYB sum to pi. So yes, indeed, quadrilateral AXDY is cyclic and D lies on the circumcircle of AXY. Now let's do the projective. We start the projective off with this lemma from EGMO. Chevians induce harmonic bundles. Let ABC be a triangle with concurrent Chevians AD, BE, and CF, possibly on the x tensions of the sides. And line EF meets BC at x, possibly at a point at infinity, then XDBC is a harmonic bundle. So in this case, points E and F are y and x respectively. So if we extend line XY to meet BC at point T out over here, then we get a harmonic bundle. In other words, TBZC equals -1. The cross ratio of 4 points on a line TBZ and C in that order. Again, if you don't know projective, go watch my YouTube video from November 18 of last year. It's 2018 Amy 2 problem 14. I explained the basics of projective there. Feel free to watch that video if you don't understand projective geometry yet. Then come back to watch this video. I'll go on anyway, assuming you know projective. So yeah, the cross ratio of TBZ and C is -1. And we can do perspectivity, meaning we can project from a line onto the circumcircle of AXY. We can do this for both points X and Y and see what we get. We can get a harmonic quadrilateral. And that would be interesting. So if we do perspectivity centered at X, line TX intersects the circumcircle at point Y. So projecting through X to the circumcircle of AXY, it's going to give us T maps to Y, B, that goes to point A, point Z, ZX intersects the circumcircle at P. So that's point P. And CX intersects the circumcircle at point D. So YAPD is harmonic. And projecting through point Y, TY intersects the circumcircle at X, BY intersects it at D, ZY intersects the circumcircle of AXY at Q, and obviously CY intersects it at A. So both quadrilaterals YAPD and XDQA are harmonic. And there's this one interesting property of harmonic quadrilaterals. I mentioned this in one of my previous YouTube videos from last year. It was the mock Amy problem 15, I'm pretty sure. But basically, if we have a harmonic quadrilateral and we consider the tangents to its circumcircle at the opposite points, like in this case, for quadrilateral YAPD, we consider the tangents at A and D, they would intersect on line YP. So basically, the tangents to the circumcircle from two opposite points would intersect on the line through the other two vertices of the quadrilateral. You'll see what I mean when I draw the tangents at A and D. So if we draw this in, the tangents from A and D intersect here. But because quadrilateral YAPD is harmonic, they also intersect on the line YP. But also, due to quadrilateral XDQA being harmonic, they would intersect on line XQ. And there's only one point that lies on both lines, and that is indeed the intersection of the tangents to the circumcircle of AXY at A and D. The only point that lies on both lines PY and XQ, which is defined to be point K. So there you have it. Point K is the intersection of the tangents to the circumcircle of AXY at points A and D. Now, you might notice something interesting about this configuration we have here. Quadrilateral PXQY, if you can see, we have it in its complete form. The opposite sides are extended in both ways. PX and QY are extended and they meet at point Z. And similarly, XQ and PY are extended and they meet at point K. And we know always by Pascal's theorem that the 4 points, 2 of them formed by the intersections of the extensions of opposite sides, and the other 2 points are the intersections of the tangents to the circumcircle at opposite points. So for example, the other 2 points I'm talking about here would be the intersection of the tangents to AXY at X and Y, and the tangents to AXY at P and Q. Oops. Those 4 points, the 2 points I just mentioned, in addition to points Z and K, all lie on the same line by Pascal's theorem. But we already know 2 of those lie on line BC. Well, the first one is obvious. PX and QY, their intersection is Z, which lies on line BC by definition. And the intersection of the tangents at X and Y, well, that would be the point Z prime, such that triangle Z prime XY is equilateral. And it's very easy to see why. Because the tangents, basically, Z prime XY is equal to angle XAY, which is equal to 60. And a similar thing goes for angle Z prime YX. That's also equal to angle YAX, which is 60. So both of these angles are 60. The angle at Z is forced to be 60 as well. Therefore, it's equilateral. And by symmetry, point Z prime lies on BC. It is the unique point such that BZ prime equals 5 and Z prime C equals 3. So we know that both Z and Z prime lie on BC, and since all 4 points are collinear, point K lies on BC as well. So it is the intersection of the tangent to the circumcircle of AXY at A and line BC. Yes, point K does indeed lie on line BC, and it also lies on the tangent to the circumcircle of AXY at A. So this point right here is point K. We'll use linearity to find the power with respect to the circumcircle of AXY. And I'm going to do this by being a little fishy and coming up with a circle of radius 0 centered at the midpoint M of BC. Now, how does this help? Well, we know that the power with respect to the circumcircle of AXY minus the power with respect to that fishy circle of radius 0 is always a linear function. So we can find where K is in terms of points B and C. And it's pretty easy to find what f of B and f of C are, if f of x is that function. We have that f of B is equal to, remember, the power of point B with respect to the circumcircle of AXY minus the power with respect to that fishy circle of radius 0 centered at M. It's 3 times 8 minus bm squared, which is 4 squared, and that's 16. So it's 24 minus 16, that's just 8. F of C is equal to 5 times 8 minus 16, which is 40 minus 16, and that's 24. And finally, f of K, well, that's just Ka squared minus Km squared. Using a right triangle, that's just Am squared. And this is an equilateral triangle with side length 8, so Am is just 4 root 3, and 4 root 3 squared is 48. And now we can use linearity. We know that 48 minus 24 over 24 minus 8 is equal to K minus C over C minus B, which is just KC over 8. 48 minus 24 is 24. 24 minus 8 is 16. And so we get KC is equal to 12. There we go. That's 12. And now KX times KQ is none other than the power of point K with respect to the circumcircle of AXY. That's just Ka squared. And we can find that by using the law of cosines on triangle KCA. We have that Ka squared is equal to Kc squared plus Ca squared. And using the 120-degree angle, we just have plus Kc times Ca. And this is easy to find. That's just 12 squared plus 8 squared plus 12 times 8. 144 plus 64 is 208. And 12 times 8 is 96. 208 plus 96, that's equal to 304. And we are done. The answer to this problem is equal to 304. So thank you all for watching this YouTube video. Please follow our channel if you would like to see more videos. And good luck on the Harvard-MIT Math Tournament today.